Okay, good morning, everybody. So for today, we will be doing the practicum on reactor power calibration. So hopefully all of you are ready to do this practicum. So in this practicum for today, I will explain a little bit about the how we do the reactor power calibration and then why we have to do it. And then after that, we will do the experiment, which will take around 40 to 45 minutes. And then after we have the data, we will analyze the results, and then we will have some discussions on the results of today's practicum. Okay, right now I will start and share the presentation for today. So here today, I will present to you about reactor power calibration. So this is like yesterday, we will be connected through the Internet Reactor Laboratory through the IRL kartini.batan.go.id. Today is February the 16th, 2021, and it is done in PSTA Batan, which is situated in Yogyakarta, Indonesia. So first of all, I would like to explain to you why do we do reactor power calibration. So we have to do reactor power calibration because we do this to calculate the real power output that is generated by the reactor. So as we know from the previous experiment, in the Cardinal reactor, we have two systems to know the power output of the Cardinal reactor, namely using the compensated ionization chamber, which is connected to the NP1000, which outputs the power in linear from 1 kilowatt to 100 kilowatts. And also the fission chamber, which is connected to the NLW2, which is outputting the power output in logarithmic. So from 10 to the power of minus 8 to 100 kilowatts. So here we will try to calculate the real power output that is generated by the reactor core, and then compare the power that is generated with the indicated power level with the power that is generated in the reactor core. So why do we have to do this? So first of all, this is done to increase the safety of the reactor. By doing this, we can be sure that the power generated does not exceed the limitations of the equipment that we have. So even though our reactor is operated conservatively, so we have a 1250 kilowatt design, but it is operated at 100 kilowatts. But if we exceed 100 kilowatts, there may be some degradation to the equipment that we have inside of the core due to the excess heat and power generation, and also the excess neutrons that may compromise the safety of our operations. And to increase efficiency, this is done so that when we operate, so for example, if we want to do an irradiation of 100 kilowatts, so typically when we do irradiation at 100 kilowatts, the neutron flux at the center of the reactor is around 10 to the power of 12. So if we have an inaccurate reading of the power level, we may be under irradiating or over irradiating the sample that is irradiated in our irradiation facilities. So to increase the efficiency, it's not only done in research reactors, but also in the nuclear power plants. So in the nuclear power plants, if the reactor is designed for 1,400 megawatts, and then they do not do the calibration of power, they may be outputting the power level at 1,400 megawatts, and it is over the actual requirement from the government. So they are just generating electricity that is not used. Therefore, we do this to increase the safety and also to increase the efficiency of the reactor. So there are two methods in doing reactor power calibration. The first one is by measuring the reactor neutron flux. So typically, this is done in nuclear power plants to do the measurements of the neutron flux. So as we know that the neutron flux is almost linear to the power output of the reactor. So they have a dedicated detector which they calibrate properly, and then they know how much flux that goes through inside of the reactor core, and that value should correlate with the power output generated by the reactor core. The second method that can be done in research reactors are named calorimetry. There are two methods of calorimetry. First of all is stationary calorimetry, and the second one is non-stationary calorimetry. In those two methods, they are similar, but they have some differences in the way we conduct the experiments. So one of it, we turn off the cooling mechanisms for the reactor, and while the other, we just take a look at the flow rate and compare the flow rate with the differences in the heat exchanger efficiency in taking the heat, and then we can calculate the power generated by the reactor. So this is the basic equation of what we are going to do today. So first of all, this is the equation for the power generation. So here, power is the macroscopic cross-section of fission divided by 3.2 times 10 to the power of 10 integrated by the flux from 0 to the volume of the core itself in watts. So basically, we know that 3.2 10 to the power of 10 is the amount of fissions needed to create 1 watt of electricity. So using this equation, we can know the power of the reactor itself. So here we can convert, if we know the flux, we can convert it into the power using this equation like this. So here I would like to explain a little bit about the differences between the different methodology of power measurement. So the first of all, we calculate the core flux using a measurement. So here we measure the neutron flux inside of the core using a detector, where using the detector we will obtain the number of fissions per second per volume unit. And then because we know that 3.2 times 10 to the power of 10 fissions per second is equal to 1 watt, we can obtain the power of generated by the reactor core. And the second method, using calorimetry, it utilizes the heat generated from uranium 235 fission. So the heat generated will heat the water, and then from the water heating, there will be some changes in the water temperature. This is the one that we will observe, and from the changes in the water temperature over a period of time, we can obtain the power generated by the reactor. So calorimetry is based on the Black principle. So in this Black principle, heat will be transferred from the hot body to the cold surrounding. So assuming that the reactor core will transfer the heat to the water and will not release the heat to the surrounding environment, we can assume that all of the heat generated will be totally used to increase the temperature of the water. And as I said before, there are two methods, stationary and non-stationary. So using the flux measurement method, this is a rough example of what we do right now in typical normal operations. The detector, either the fission chamber or the compensated ionization chamber, will be inside of the reactor core, where inside of the reactor core, when during operations, the control rods are raised. So there are neutrons that creates a neutron flux here, and then they will interact with the detectors, and then they will create a signal output, which is gained by the preamp and amplifier, and then they will be converted into the power levels using the instrumentation system, either using the NP1000 or the NOW2. Using calorimetry, this is the other method. The heat source will cause an increase in the water temperature because this is a method that uses a lot of assumption, because we have to assume that all of the heat will only increase the temperature of the water, but not be released to the environment through evaporation or through the walls of the tanks. Here, using that assumption, the water will be heated by the reactor core and cause the water to heat up, and then the differences will be picked up by the thermometer, and then we will see the power generated from this thing that we do. So there are two methods of calorimetry. So the first one is using the stationary calorimetry. Using the stationary calorimetry, the system that we use is using the primary cooling system that is still remains on. And here we only observe two things. The first thing is the flow rate from the primary cooling system. So as we know from the previous experiments, during our operations, we have pumps that will circulate the water from the primary cooling system and into the heat exchanger. We will see how much the flow rate of the primary cooling system from going in and out of the heat exchanger. How much is the flow rate? And then we will also see the inlet and outlet temperature from the heat exchanger. So here we see that the power generated is equals to the primary cooling system flow rate multiplied by the heat capacity of water multiplied by the differences in the temperature in the inlet and outlet from the heat exchanger. So this is the most simple part, but this is can only be done in certain reactors, and this cannot be done at our reactor in Kartini because the flow rate at the Kartini reactor is comparatively relatively low. Because of this low flow rate, this will not create an accurate calculation using this method. Using the non-stationary calorimetry, the primary cooling system will be turned off, where at a constant power level, all of the heat will accumulate, making the water hotter, and then we see the differences in the temperature using the thermometer. Using this, we have to try to maintain the maximum water temperature at 40 degrees Celsius, because if we have the water above 40 degrees Celsius, when we turn on the primary cooling system, we may cause some damage into the demineralization system, because the resin and the filters of the demineralization system, they are a lot more sensitive to the changes in the heat. Therefore, if the temperature of the water gets too high, they may damage the filters and the resin inside of the demineralization system. Besides that, having a high water temperature may increase a little bit of the fatigue of the materials inside of the reactor tank, and it may increase the rate of aging in the reactor tank. Here, the energy from fission is equal to the energy received by the primary cooling system. So here we have the assumption that none of the heat is released through the evaporation of water, or there is no transfer of heat from the water to the tank or from the water to the reactor grid internals and so on. So this is the equation that we use for non-stationary calorimetry, where the real power output is equal to the differences in the heat generated in the reactor over time, where this is equals to the water value of the Cartini reactor, which is 19.0476 kilowatt hours per degrees Celsius, time multiplied with the differences in the temperature over a period of time. So we obtain this value of 19.04676. This is done from experimental data. So here, the previous workers at the Cartini reactor, they have done some experiments to obtain the water value of the Cartini reactor. This water value, in quotation marks, they take into account the materials, the heat capacity of the materials inside of the reactor. So they also take into account, say, the reactor grid, and then the reactor stand, the cooling, sorry, the reflectors, and then the lazy Susan, and the other components inside of the reactor core. And they came up with this value for the heat capacity, and they will obtain the water value of the Cartini reactor. This value might be different between each reactor, so the values here at the Cartini reactor may be different with another Triga reactor operating at 100 kilowatts, but with a different components inside. So this is different for each reactors. So for today, what we are going to be using is simple. So we are just going to be using a thermometer and a stopwatch. So the thermometer that we use for today, there are 3 thermometers. So the first one, we can use the data from the IRL Cartini data, and the second one is from the process computer. So here we look at the ATR temperature. So this is for the second data. And for the third one, we have set another thermometer. I'm sorry, it's still blurry, but our operators are still trying to keep it in focus. So yeah, this is the thermometer, and you can see the temperature. So hopefully there will be 3 data that you can take. One from the IRL Cartini website. The second one is from this thermometer. And then the third one is from the process computer. This one. So there will be 3 data sets that you can take. So maybe for the analysis, you can compare between each thermometer that we use. But you can also just take one and try to elaborate the data from this. Continuing to my presentation. We also need to have a stopwatch or a clock, because we need to have a good consistency in when we take the time. So typically we take the data every 5 minutes. So if you take the data not consistently, so for example, one is taken in the interval of 4 minutes, and then you take it after 5 minutes, and then you take it after 6 minutes, even though in 15 minutes you have 3 sets of data and it averages at 5 minutes, because of the data is not taken consistently, there may be some inconsistencies in your calculation. So it will be better if you have a stopwatch, or you have your cell phone, you have a timer, and you can put the alarm or something, so that you can take the data at regular intervals with an accurate intervals between data taking. So we typically take the data every 5 minutes for 9 sets of data. So it will take around 45 minutes. So for today, after we finish the explanation for today, the explanation of the practicum, we will take the data for around 45 minutes, and then we will discuss the results. Okay, the next one. Besides, these are the instruments that you can take. So as previously mentioned, you can take a look at this value. So the ATR temperature. So besides the one from the IRL website, you can also take this data. Just be careful to not mix the data with either this data or the primary cooling system data, or it will be very, very chaotic if you take the data for the IFE temperature data. Masya Allah. So these are the data sets that you can use. And for the using the IRL website, you can take the data from this one. So you just take sure to the reactor water tank temperature. And if you want, you can also compare it with the actual power level from the NP1000 and NLW2 when you download the data, so you can have a rough average of the power level. So because as we know that neutronics, they go random. So there are some random fluctuations in the power level. Sometimes it dips a little bit, and then due to the negative coefficient of temperature of fuel, it will sometimes the power will go down as the fuel heats up, and then after the power level goes down, it becomes cooler, and then the power will raise a little bit, and then there will be some fluctuation. So maybe in the analysis, you can also compare the calculations with the average from the data from the NP1000. So this is another part that you can write in your report. So for the procedure for today, what we are going to do today is first we will operate the reactor at 100 kilowatts, and then we will turn off the primary cooling system. And after we achieve a constant power output, we will start to observe the water temperature with a 5-minute interval, and then we will compare the results with the indicated power level. So for today, we will do the power calibration at 100 kilowatts, but here we can also do the reactor power calibration at 50 watts. So we can actually do some variation in the calibration power. So we can have a good curve about the power level comparing the increase in power using the instrumentation system and the power level using the power calibration method using the calorimetry. So you can compare from say 50 watts to 100 watts, and then after 10 kilowatts interval, so say in 60 watts, you can compare at using the NP1000 and the calorimetry, and then at 70 watts, so you can have a graph plotting the system. But for today, we are only going to do the procedure at 100 kilowatts. And we will be comparing the data between the NP1000 and then the 3 thermometers, which are the IRL website, and then the process computer, and also the physical thermometer that we have on our camera. So this is a form that you will be filling, but while we wait, we will make an Excel sheet so we can easily analyze the results. So basically, you have to make an Excel sheet indicating the time. So from 0 to 45, and then the temperature from thermometer A, thermometer B, and thermometer C. So from the IRL website, and then from the process computer, and then from the thermometer. So to do the analysis, it may seem quite complex, but basically we only need to have a regression of the results. So if you want to do it like this, feel free to do so. So it may take a long time and a bit complex, but it will be a lot easier if we just do like this. So when we plot the data from time to the reactor water temperature, we will have a graph on the distribution of temperature, and then we can just add the trend line and then show the equation, and then we will have the gradient of the data. So for example, in this graph, we have the gradient at 0.0747 and with the R square of around 0.9798. Well, this is not as good as what we can obtain. So the higher the R square, or when it is near to 1, the better. So this is good enough, but not that good. This is just for example. So from here, when we get the gradient, we have the dt changes in temperature over the changes in time. We will just have to multiply this value with the water value of the Carteni water. So the water value of the Carteni water, I would like to remind you, is 19.0476. So we multiply this value with 19.0476, and then we will get the power level in kilowatts. So in summary, the reactor power calibration is done to know the actual power level output generated compared to the value that is shown by the instrumentation system, which is shown in the meter. The power level measurement at the Carteni reactor is done using the reactor flux measurement, which is calibrated by calorimetry. And there are two methods of calorimetry, which are stationary and non-stationary, where both are based on heat transfer.